Okay, I'm very excited to be here. Thank you for coming to my talk. Today, I'm going to take you on this short journey of life of a container. And my name is Indradhanush Gupta, and I'm a programmer at Loodse. And I've been programming professionally for about 6 years now, and I've been using containers for nearly the entirety of the time. And I asked around very early into my programming career that what really is a container, and the initial response was something along the lines of, oh, it's very similar to a virtual machine, but only that it does not have its own kernel and it shares the host's kernel. And that felt very magical to me. And this quote from Sir Arthur Charles Clarke felt very relevant, that any sufficiently advanced technology is indistinguishable from magic. Containers felt like magic to me. And as a result, I see myself as someone who likes to take things which look very complicated at the first or second glance and try to find a way to see that is there a way to find and represent it as something much simpler, right? And that begs the question that what is a container? Well, spoiler alert, there is no such thing as a container. Yeah, there is no such thing as a container, and that's pretty much the end of the talk. So that's probably the shortest talk here. So thank you for coming to my talk. I'll be hanging outside for questions. OK. I don't know if you bought it, or if you clapped for that, I thank you for that. So I was just kidding, right? And so seriously, what really is a container? And when I looked around, it's made of two unique concepts called namespaces and Cgroups or control groups. We'll look into each of these, what these concepts are. But before that, let's just try to understand how are processes created in a Linux box or a Unix box. At the start, you will have something like a parent process. This parent process can be your shell terminal or your application which is spawning new processes. And the system call to create a new process is called a fork. When you make a fork call, two things happen. Number one, a child process comes up. Number two, the parent process gets a child PID or a child process identifier. Now, this is very important so that the parent process can keep track of its children, literally. It doesn't want to lose out all its children. And as time goes on, the child process goes ahead with its normal execution and gets terminated, and so does the parent. So now that we understand what a parent process and how a child process interact with each other, or how they control, how the parent process controls the child process, let's try and understand what a namespace is. But quick plug, I wrote a detailed blog post a few years back on how the fork works exactly. So there's a much detailed explanation there. If you're interested, feel free to check this link out. And in the meantime, we'll come back to what namespaces are. So namespaces are an isolation primitive for resources. And namespaces are isolating 7 kinds of resources. I will not go ahead and explain each of them, but to give you an idea of what they do is if you have a network namespace, it helps you isolate your network resources. So in a way, it simulates 2 different computers with 2 different network interfaces in the same computer. And how does it do that? So let's go ahead and quickly go into this demo. So if you will, please pray to the demo gods for me. What I have on my terminal here is 2 independent shell processes. This command gives the process ID of the shell processes that I'm running. And to start a new process, what I will do is I will run the unshare command. It unshares the network, it unshares the namespace from the host namespace. There's something I forgot to mention is that when our system starts up, it has all the default host namespaces already set up for you. So right now, both the shell processes are running on the exact same namespaces. But you do not have to take my word for it. You can just verify it, right? So before that, let's just quickly take a look at what are the processes running, what are the namespaces of these processes. So we'll take a look inside the proc directory, which is a directory that keeps tracks of all the processes currently running on your system. And to do that, we do this, and this lists down all the independent processes like cgroup, IPC, mount, net, PID, etc., etc. And it points to something that looks like a weird number string thing. This thing is your namespace ID. And this is unique for each independent namespace. But if we do the same command in the shell that I have in the lower split, we'll see that it's the same. For example, for Cgroup, it's 4026, whatever, ending in 1835, right? So quickly, let's just examine the network namespace, because that's the namespace we are concerned about. So right now, they're running in the same network namespace, which is the host network namespace. I will run the unshare command with the flag /-n, and that will create a new network namespace. And once again, don't take my word for it. Let's just quickly do that. See, there's a different number there, right now, right? 3324. This is a new namespace. Now, there's a command called ipnetns_list that lists down all the network namespaces on your system. But it doesn't show any network namespaces right now. We just created one, right? We see. So what is happening here? Like what's going on? Like if there's a new network namespace and it does show up, that's weird, right? Now the trick to this is the IP command looks for namespaces in a certain directory. And to do that, the directory would be var run_netns. Let's create a directory called child. Now let's run the command again. There's an error. Demo is not failing yet. It says that peer netns reference is invalid. We've created a directory, so the IP command can find the directory, but it cannot find a process which is mapped onto to use the namespace. So to do that, we will let's also make this easier to understand. This is just for the demo, just usually don't use it, just easier to keep track of. So what we want to do is we want to bind mount the oh sorry, that would be net. So that's the file that this process is using to map its network namespace. It points to a specific namespace ID. If you remember that weird Cgroup/ID thing, that's what this is, right? So we will mount this to the not that child directory, and now magically it finds the namespace and there is no error. Now there's two different namespaces, but what does that mean? If in my host namespace, if I pinged this would work, right? You expect this to work. I mean, this is the one thing you always expect to work, but doesn't network is unreachable? What? I mean, what's going on? So let's look at what are the network interfaces. There's just a single loopback interface, and if you look closely, the state is down, and does not have an address associated. So this namespace does not know where 127.0.0.1 exists. And you would have to add an address to this interface, and only then it knows, okay, where is this interface and how to reach it, right? And in this demo, what we're going to do is we're going to make these two namespaces, the host namespace and the child namespace, talk to each other. And to do that, the first thing we're going to do is we will create a pair of virtual Ethernet devices. There's no real network interface card, just a pair of virtual Ethernet devices. And we'll do this on the host network namespace. So let's just quickly do that. veth. So we want to create a device called veth0 of type veth, which is virtual Ethernet, and its peer's name, which is the other side of the tunnel, if so be it, is called veth1. Now let's take a look at the devices we just added. We have two virtual Ethernet devices, and if we go back and do the same thing here, we don't really have it because we added this new interface in the host namespace. Now we want to put this interface inside the child namespace. So how do we do that? To do that, we are going to set this eth1 device into the netns called child. Pretty simple. IP link set veth1, set this device inside this specific namespace. And if you look for it again, now we have both the independent interfaces. Wait, hold on a second. Yeah, okay, that makes it easier, I hope. Again, they don't have any address associated with it. They do not have any, their state is also down. So you have just, if you think about two computers, you've barely just plugged in your network interface card, and it's just there. You haven't yet configured it. So let's quickly go ahead and configure it. We are going to add an address as the first thing to device v@1, and we're going to give it the address 8.2.24, and on the, and we'll do the same command on the host network namespace, and this time give it the address 8.1/24, and you can verify it if you looked at, there you go. Now we have an address, and it's identified by 10.16.8.1. Same thing on the child network namespace as well. It has an address 10.2, but it's still not up. So there's just one last thing to do, which is set, this one is pretty simple, up. Oh, okay, this one is called v@1. Naming is the hardest thing, folks. And let's just ping the other side of the tunnel, and we are able to ping it, and from the other side. So both ends are now sending packets to each other. And if you try to ping to something like 8.3, it doesn't exist. There's nothing at the end of it, and your computer is going to be like, I don't know how to find that. So coming back to the slides, what we just did can be very well explained by this image. It's just two children, literally two children, talking over each other with a string telephone. And you can think of the children as the network namespaces, and the 10 canisters that they're using are the virtual Ethernet devices. So if the demo was too hard to absorb, I get it. It's a lot to get. It took me quite some time. I hope this gives a better understanding of what we just did with two network namespaces. In technical terms, we simulated two different devices on the same computer. So now you can run two different processes in both the different network namespaces, and they can talk to each other as if they were two different computers. So if you're testing, I don't know, like something like a client server thing, and you want them to have different addresses, you don't need to go and like provision a new cloud machine, cloud instance. You can just create a new network namespace, test it out. Moving on to Cgroups. While network namespaces helps you isolate the resources, what Cgroups does is control how much of those resources you're going to allocate, which is, for example, CPU or memory, and there are a few other resources, but the easiest to explain are CPU and memory. So once again, let's just quickly go on to the demo and see what's going on here. In this case, I will create a new host namespace, which means I can have my own host name. So I will not bother setting it right now. It's just a new namespace, and the Cgroups exist in the sysfs directory. So you can look at what are the available Cgroups on your system. Usually by default they're mounted on your system. If they're not, you'll have to do some additional work. But assuming that they're already mounted, you know that, okay, you have things like CPU, you have things like memory. And to create a new Cgroup, it's as simple as creating a new directory. Stay with me. So I want to create a new Cgroup for memory. So I will create a new directory under the memory path, and let's just call it demo, right? And we just created it, and if you look inside this directory, there's a host of files. I did not create it, right? I did not create these files. It got created on its own. So what Cgroup does is the moment you create a new directory under whatever controller, memory controller you want to create, what it did is it creates all the necessary infrastructure, all the necessary files that you need, and these files are going to tell you everything about the CPU, about the Cgroup. So let's take a look at, for example, limit in bytes. That's bytes. That's a lot of bytes. It's probably a gigabyte or something like that. And to test this out, what we can do now is change this to a smaller number, let's say about 4 MB. So that's about 4 followed by 6 zeros in bytes, if my math is correct, which rarely is. And we're going to write this. And let's just verify that again. It rounds it down. Honestly, I don't know why. I think that has something to do with the memory architecture. So it rounds down to whatever the latest memory address is without, like, you can't take half a memory address. So it allocates something about 4 MB. And let's just quickly verify that. Divided by, so that's kilobytes times megabytes, less than 4 MB, right? We're happy with it. And let's try running a command like, I don't know, wikipedia.org. It failed because I don't have internet right now. But so it just worked in a way. If I had internet, this would have worked, right? But how do I get this namespace or get this process to be limited by the C group I just created? The way around that is there is yet another file. Linux is all files. I had a difficult time understanding that previously, but it gets better now. And there's this file, and the contents of this file is empty. You write the process ID of the process that you want to be limited by the C group, and your job's done. So let's just echo the process ID into this. And for your verification, that's 6416446. And you have two process IDs right now. One of them is the process ID we entered. The other is the cat command we ran. So by default, inside a namespace, if it's already part of a C group, any new child processes will by default get added onto the C group. So next time if you run this command again, 64212 won't be there if there's 213. So moving on, now that we've added the process ID into the C group, I would expect this command to fail. Please fail. Yes. Killed, right? What just happened? Like, what just happened? Like, why would it kill it? Because you've told the C group that no process running inside this should be able to use more than 4 MB, approximately. And whoa, that was not planned. OK. I think, yeah, so. And as a result, the operating system does not allow that process to use more than 4 MB, and it just kills that process. Like, wait there, you're not allowed more memory than this, or more CPU than this, and just stop, get out of here, and game over, right? And so now, if you look at containers, if you use Docker, how many of you have used Docker, I suppose? How many of you have used Docker? How many of you have tried to like limit memory and limit CPUs on a Docker container? A few of you. So what it's doing behind the scenes, not this, what it's doing behind the scenes is it's using C groups. When you use something like you want to expose a new port, Docker container is running in a new network namespace. That's what is happening. The first demo of the day. That's what is happening. So it's really, really not that complicated. Implementing it is, of course, challenging, which is why we need things like container runtimes. And that is why there's a lot of things. And there are few more things which I do not have enough time to demo, but I will talk about them, which are capabilities and seccomp. Capabilities helps you to limit your root privileges. Now, sometimes you might want to run an application with a privileged, with some extra privileges, right? And if you run it as root, the problem there is the moment you're running a process as root, it has all the power of wreaking havoc with your system. Maybe accidentally, maybe not accidentally, and you don't want that. What you want is you want to limit their whatever they can do bad, that limit it. Like, you need only network operations. That's the only capability you are going to have. You don't need to create new processes. You don't need to manage other processes. You're not going to have that. So that lets you do with Linux, lets you do with capabilities. And capnet admin here as one of the example. You give this capability, it gets the ability to manage your network interfaces and other network related operations. And the second one is seccomp, or secure computing. It limits the use of system calls itself. So for example, unshare, kill, or even something like CPU, there's something, okay, I forget. But unshare and kill are one of the examples. So you cannot use these system calls. So you can block certain system calls to make your environment more secure. And Docker or other container runtimes, they have this ability to implement seccomp. And in a way, this helps you form an isolated, restricted view of what is really your operating system. And it's not really magic at all. And if you remember this diagram from earlier in the presentation, it is admittedly slightly incomplete. There is one more thing that the parent process does, is it waits for the child process to terminate, which is why it needs the child PID. And what it does is once the process has terminated, it makes sure, the parent process makes sure that the child processes, the resources belonging to the child process are cleared up, or else if it doesn't wait for this child process to terminate, what you then have are zombie processes, and then you have leaked resources on your system that are not being used by anyone, that are not being allowed to be used by anyone. So in a way, this is a very high-level diagram of what a container runtime does for you. It starts the container runtime engine, or whatever the term is, and it runs new child processes which are containers, and it waits for them to terminate, and then it comes back and it cleans up, and then you are able to run containers in your system. And that is all. So we will do a quick recap. Might have been a bit too much. So you have namespaces, which isolates the type of resources. Cgroups, which limits the resources. This is one of the most confusing things that I was struggling with when I started out. So namespaces is the type of resources. Cgroups is the amount of resources. That's the keyword you want to look for. And then you have capabilities to reduce the risk of misuse of root privileges, and seccomp is to block unwanted syscalls. And in a way, that's pretty much it about a container runtime or containers. So that doesn't seem very complicated anymore, does it? And I was able to find a lot of information over the years in these links. The first one is namespaces in operation. It's an amazing series of blog posts. Explains all the namespaces but Cgroups. I think Cgroups was not there when this series was published, but these 6-7 articles is like amazing. Take your time, read through it. And of course, Julia Evans says what even is a container is like a brilliant explanation. And there's something you just cannot get around is man pages. When in doubt, man page. And with that, we come to the end of this talk, and this time for real. Thank you.